So, last time we asked a question that instead of taking this usual curved lines for the phase diagram, what will happen if we take the straight line for the curve for this phase diagrams, particularly for the solidus and the liquidus line. Well, if you look at it closely, what you would see is that it makes the biggest difference to, or in fact which is why we take this assumption, is because this partition ratio K, if you take at any value now, any temperature value, it remains constant, and you can easily prove this using similar triangle principle. So, this is a similar triangle, this is a similar triangle, this is a similar triangle, and therefore, K will equal to Cs by Cl remains constant. So, that is why we have assumed, or we assume for our understanding and for formulating the relations, that these solidus and liquidus are straight lines. So, the straight line liquidus and solidus leading to constant K. So, these are some of the assumptions that we make, but other than this assumptions, for the sake of simplicity, you would see what we will do is that we will always be assuming the left side of the phase diagram. If you want to talk about B in A, then you put A over here and say B is the increasing fraction. If you want to understand about A in B, then you put B over here and say percentage fraction of A. So, that does not take away the generality of this whatever we talk about later on, but what it does is that for the, again for our sake of simplicity, it ensures, or it makes sure that K is always less than 1, because we are always on the left side. So, this is Cs, this is Cl. So, Cs by Cl will always be, Cs is less than Cs. So, therefore, Cs is less than Cl. So, the K will always be less than 1. So, this is not really an assumption, but you can say some certain kind of simplification where we are not losing generalization. We still get all the things, we do not lose any of the information, we are just keeping it like this, so that it becomes simpler for us. Okay, so, having said this, we are looking at certain conditions. Now, the solidification that will take place, if you look at the phase diagram again, it will not be very simple. Just as a simple example, look at this. Okay. So, let us say this is our C naught, this is the composition of the alloy that we want to solidify. At this particular point, when the first solid forms, the composition of that solid according to our first assumption of equilibrium at interface will have a composition like this. And what will it be? It will actually be equal to Kc naught. So, the first solid that forms will always have the composition Kc naught, because the liquid when it comes to this liquidus temperature, at that point the solid will have the composition Kc naught. Cs by Cl is equal to K. So, the solid composition is equal to Kc naught, which is the C naught is the liquid composition. Now, as you lower the temperature at this particular point, the liquid will have a composition like this and the solid will have a composition like this. So, the solid that forms at that particular temperature will have a composition like this, Cs, let us say Cs1, somewhere over here it will have Cs2 and so on. This is now you can see that although the overall composition that we have talked about should have over the composition as C naught, and we would have assumed that the solid and liquid would have equilibrium, the overall solid will have that kind of composition in the single phase, but the way the solid is forming, it has changing composition at different point in temperature, and hence it leads us to ask question, is some kind of homogenization taking place in the solid is some kind of homogenization taking place in liquid? Yes, then what kind of homogenization? So, based on those homogenization we will get very different solutions for different conditions. So, we will begin with a condition of what is called as equilibrium solidification. Okay, one more assumption that we will be talking about in most of these cases, I have not, again those are not explicit assumption, is that it is you can say a one dimensional solidification. Why I just introduced it, because we have the way we will draw the composition profile, you would see that it is a one dimensional solidification, and this particularly for plane front solidification, this one dimensional solidification would usually be done for growth of single crystals, because plane front solidification is very slow process, and it is done only to achieve single crystals, single crystalline samples. So, again that is what we are doing is solidification of a single crystal, and for that we are taking different assumptions regarding what kind of homogenization you will see in solid, what kind of homogenization you will see in liquid, and we are here at equilibrium solidification. Now, what does this equilibrium solidification mean? So, let us say this is the kind of a rod that you want to solidify. This will be single crystal in the end, but at some stage it will be all liquid, then it will become solid and so on. So, let us say at the beginning it is all liquid, and therefore, at this particular point we are somewhere. So, let me draw this now with respect to our equilibrium concentration. So, if your temperature is above this point, this whole thing is liquid. Now, just at this particular temperature, which is your T solidus, sorry T liquidus, at this particular temperature, what will be the composition that you would see for this? Okay, let me draw it over here. This is the composition. This is let us say we call it in fraction, whatever length it is, will this f will be equal to 1 over here and f will be equal to 0 over here. This is the equilibrium, this is the composition we have taken C, and on the y axis this is concentration, and what we are trying to draw is solid concentration, how the concentration of solid will look like. So, the first solid that forms, what is the composition? We said earlier it has to be Kc naught. So, this is the first solid that forms Kc naught, but it is only at a very small length over here, and this is the rest of it is still liquid. So, this part is the solid, a very thin region, and rest of it is approximately equal to liquid. So, we will say this is Cl is approximately equal to C naught. Now, let us decrease the temperature a little bit. So, we are at this temperature. At this temperature, let us say this is our composition, which is equal to, we said earlier, let us say this is CS1, this is Cl1. So, we will keep the axis similar to earlier, and now over here this was your C naught this was your Kc naught, and somewhere in between C naught and Kc naught, you see this is the CS1, this is somewhere between C naught and Kc naught. So somewhere over here you have the solid concentration, which is CS1, and this is your liquid has also, composition has also raised, you see 1 above C naught, it has become Cl1. So this is Cl1, the liquid concentration. Now it is very easy to understand that the overall liquid concentration increased because diffusion in liquid is very fast. But what we are also assuming when we say this equilibrium solidification is that the concentration of the solid part also gets very fast homogenized. This part, the original solid that formed was at Kc naught, but by the time the solidification reached to this stage, we are assuming that the overall concentration has also reached this stage. The liquid that formed at that particular temperature should be of this concentration, but we are assuming that the inside the solid, the diffusion is taking so fast that this point inside, any point beyond this inside the solid is also at this concentration. Similarly, if you keep going further inside the solid or further solidifying it, so now let us say we are at still lower temperature, so we are at Cl2 and this is CS2. So this was C naught, we started with Kc naught, we reached CS1, and then even higher than CS1 is some composition CS2, and this extends for a longer region, so somewhere like this, and the composition of Cl liquid has increased even further, Cl2. So again, like I said, it is very easy to understand the homogenization in the liquid part. So the liquid has become homogenized, it has concentration Cl2, but what is interesting or what is inherent or what is the assumption in this particular case of equilibrium solidification is that the whole solid also gets homogenized, meaning diffusion is so fast for some way, we are not talking about how and why, but diffusion is so fast inside the solid that the whole solid also gets homogenized and has same composition as predicted by the phase diagram. So everything is going as per phase diagram, there is no change or deviation from the phase diagram. And if you keep going, so here this is the length that has solidified, let us say some amount of this, over here some close to 50%. Schematically we are not giving it a number yet, or we are not doing it in quantitative way. Now let us say at the final temperature, which is T equal to Ts. So this is T equal to Ts, solidus temperature. Over here we were at T equal to TL, liquidus temperature, and in between we were at some between temperature. So we are decreasing temperature, and at this liquidus the solid that forms has the concentration equal to so the beginning structure would be very same. This is our F equal to 1, this is F equal to 0. We are looking at the length in terms of fraction. So this is the total fraction, the whole fraction has solidified. Over here 0 fraction has solidified. Here this is the concentration, this is the C naught. Now the first solid that solidifies, yes, you would have realized by now it should have concentration of Kc naught, because Cs by Cl is equal to K and Cl is approximately C naught. So C naught, and therefore this is Kc naught. Cs equal to Kc naught and Cl approximately equal to C naught. That is the composition over here. Now what happens next is very different from what we discussed earlier. Over here when the solidification starts to take place, the next solid that forms is over here, but this is only the outer layer of the solid which has this concentration. So the solidification of the outer layer goes like this, like this, like this, but not the overall concentration. When we are looking at the phase diagram in equilibrium condition, what it says is that at this particular temperature all of solid should have this concentration, not just the outer layer. At this particular temperature and for this concentration, all of liquid should have this concentration. So if you are saying Cl1, this is CS1, so at this particular temperature T1, all of solid should have concentration CS1 and all of liquid should have concentration Cl1. But what is happening is that only the outer layer of the solid that solidifies has this concentration, the inside has still concentration like this. So what will it mean? It will mean that the average concentration would be somewhere below this. If you look at the average concentration plot of the solid, it will be like this. Now there are various things that we will need to understand when we look at this, but first I have one of those things is, for example, that I have drawn it only up to Tm. Another is that I have not crossed the C0 concentration line. We will look at those reasons very soon, but for now look at this plot. So this is a continuously varying concentration, and therefore if we draw a similar concentration over here, you will see, okay, let me be a little bit, draw it a little bit better. So let us say at some particular temperature we have reached a concentration like this, and at this particular temperature the liquid will have a different concentration corresponding to equilibrium at interface. At interface it is still equilibrium. We are not leaving the assumption of equilibrium at interface. We are only saying overall equilibrium inside the solid is not at equilibrium. So this is, if this is any particular concentration Cs, then corresponding to this will be Cl. So this is Cs1, this is Cl1, and since there is complete diffusion in the liquid or homogenization in the liquid will have uniform concentration. Now once this new layer of solid forms, what happens when we go from over here this temperature to, let us say, even next temperature just a little bit below it, the solute concentration that forms at the outside has higher amount of solute. So this is the concentration of the solute that forms over here, and this is the concentration of the liquid. Now it is still lower than C0, it means it is ejecting some of that solute into the liquid. So once it ejects that liquid, that solute, it gets into the liquid, and therefore the concentration of the solute in the liquid increases further. So this is the new layer of solid that has formed, which has concentration higher than what the original layer had, but still it is lower than C0. So some amount of solute is getting rejected. And this is the increase in the concentration of the solute in the liquid. Now if we equate these two, we will be in a position to get a relation of solute concentration as a function of distance. So what is this? So let us say we are looking at a distance f prime, therefore this becomes 1 minus f prime, and a small thickness has grown, so let us call it df prime. The concentration of liquid over here was Cl. Instead of Cl1 we will call it prime, because we are putting all the variables for now at prime. So Cl1 is equal to Cl prime basically. So here it was Cl1 and it has increased by a small amount dCl1. Now the amount of solute that has been rejected from this formation of new layer gets into the liquid. So this amount of solute can be equated. The whatever amount has been ejected from solid must be getting into the liquid part. So let's see, let's try to formulate the equation for that. First let's try to find out what is the area of this, because this area represents the volume of solute that has been ejected. So this is Cl prime minus Cs prime into df prime. So this length is Cl prime minus Cs prime and this thickness is df prime, and this is equal to this area. What is this area? This is area is equal to d Cl prime into 1 minus f prime. So this is the length 1 minus f and this thickness is dCl prime. So we have set up a differential equation. Now let's try to solve it, and when we solve it we'll again invoke our equilibrium at interface. So Cl prime is equal to k Cs prime. Therefore this becomes 1 minus k Cs prime df prime equal to dCl sorry Cs is equal to KCl. I have therefore this is Cl. So now we will put the Cl terms together and we have so let me take it to this board. So we know the form. If you want to get the integrate it, then df prime by 1 minus f or dCl prime by Cl prime will get integrated into a log form. So this equation will become and this has to be integrated from 0 to 1, not 0 to 1 but 0 to some value of f, and this one will become ln Cl prime, which has to be integrated from 0 to some value of Cl, and from here you can easily come to so this is the equation, and you can further reduce it to okay, I missed something here. This is not 0 actually, this is C naught. So this is the equation that you get Cl equal to C naught times 1 minus f to the power k minus 1. Now let me put it in a form that you already know, which is in the Scheil equation form. So this will become Cs, we'll make we'll again invoke the relation that Cs is equal to KCl. So this becomes Cs equal to k C naught 1 minus f to the power k minus 1, which is called so this is the equation which describes how the solute concentration in the solid will vary starting from the point where the solidification start to take place and all the way up to the point, up to what point? That is a question that again you should ponder over, and we will come back to it in the next class. So there is lot more things that you need to think in the meantime. For example, I said that this does not cross the C0 concentration, and plus this stops at C0, and then I am also saying that there is only up to a particular value that you can use this. So all these are related, and we'll come back to this in the next class. Thanks.